This series of videos focuses on graphs. So we are going to begin with some terminology, so defining what a graph is and some of the characteristics that we'll look for in graphs. So a graph is a collection of vertices and edges. We've heard similar terms before when we talked about trees. With trees, we usually call them nodes and edges. With graphs, we usually call them vertices and edges, although you will notice that sometimes we do still call them nodes. So nodes and vertices are kind of can be used interchangeably. An edge is a connection between two vertices. And two vertices are considered adjacent if they're connected by an edge. Another term for that is neighbors. So if two vertices are connected by an edge, you can say that they are neighbors or that they are adjacent to each other. A graph is sparse if it has few edges, so lots of vertices, not very many edges. There's different ways and metrics of measuring that. One example, the example given in our textbook, is around order n of edges. That would be considered a sparse graph. A dense graph is a graph with many edges. So again, lots of different ways you could judge that, but the kind of threshold given in our textbook is n squared, on the order of n squared edges. Most graphs are sparse. Okay, so typically the kind of information we're representing in graphs, it's more likely that the graph is going to be sparse. So here's an example of a graph. This graph in particular has 6 vertices, so I've labeled them A, B, C, D, E, and F. Okay, and it has 7 edges. The edges are here as the line, so we have 6 vertices, 7 edges. A and B, for example, are adjacent vertices or neighbors. You can see that they're connected by an edge. B and C are not neighbors. They are not adjacent because there's no edge connecting them. A path is a sequence of edges that connect two vertices, so essentially a way to travel from one vertex to another through edges. A simple path is a path that repeats no vertices, so no vertex is repeated. And the length of that path would be the number of edges that you cross throughout the path. A cycle is a path with the same starting and ending vertex, and a simple cycle is a cycle that, similar to a simple path, passes only through vertices once, except for, of course, the starting and ending vertex, because that's what makes it a cycle. If a graph has no cycles, it's called acyclic. If a graph has at least one cycle, it's called cyclic. An acyclic graph is also known as a tree. So any acyclic graph is a tree. Now, be careful, it's not necessarily a binary tree, but it is a tree. That is the definition of a tree, is an acyclic graph. So here's an example of a path. This would be a simple path from B to F. We could travel from B to A to D, and D to F. So that would be a simple path from B to F, and the length of that path would be 3 because we travel across 3 edges. Here's an example of a cycle, and this is a simple cycle. It's a cycle of length 4 going from A back to itself. So we can go from A to D, D to F, F to C, and C back to A. So that's an example of a cycle. Again, it's a path essentially where we start and end at the same vertex. Edges, again, connect two vertices. Now, the examples we just looked at are examples of undirected edges. So an edge can be directed or undirected. Directed edges have a, not surprisingly, direction from one vertex to another. Undirected edges essentially just go in both directions. So you can think about them as having no direction or as really going in both directions. If you have a graph with directed edges, the other term you'll hear for that is a digraph, a directed graph. In addition to edges being directed or undirected, edges can also have weights. A weight is a value, or sometimes called a cost, associated with that edge. In a weighted graph, so a graph whose edges have weights, you can often find paths between different vertices and compare those paths by the sum of their edge weights. So a lot of times you'll want to find the cheapest path or the shortest path between vertices. In a weighted graph, the cheapest path would be the path whose the sum of all the weights is the lowest. So a lot of times, a weight, again, is sometimes called a cost because it's essentially some sort of value that's associated with going from one vertex to another. So this is the example we looked at before, and this graph is undirected. The edges go in both directions, and unweighted. The edges don't have any weights. This graph would be undirected. You can see again the edges don't have any direction, but this graph is weighted. So each one of my edges has a weight, a numeric weight associated with it. So for example, the cost of traveling along the path from, let's say, N to J would be, if we go this way, would be 2, 4, 10. Or if we traveled another way, we could go 2, 3, so that's 5, and 4, which is 9. So this would be a path with less cost going from N to J than this path, which also goes from N to J but has a greater cost. This is a digraph, a directed graph. So you'll see that the edges here have a direction. They have an arrow. And some of them are still going in both directions. So here is an example of an edge that goes in both directions. Now, once it's a directed graph, we do put the arrows on both ends. So we don't leave it just a straight line. We do put the arrows on both ends to indicate that that edge goes in both directions. But other edges only go in one direction. So this edge goes from G to H, but not the other way. So there is no edge leading this way. That doesn't exist in this digraph. So all of our edges are directed. This graph is also unweighted, so our edges don't have any weights. Now we talked about neighbors or adjacent vertices, and those are vertices that are connected by an edge. But what does that mean in a digraph, in a graph with directed edges? So in a digraph, a vertex is adjacent to another vertex if there's an edge going from the second back to the first. So vertex I is adjacent to vertex J if there's an edge from J to I. Another way to say that would be that I is J's neighbor. So looking again at our digraph example, here we can say that N is adjacent to G, or you can also say N is G's neighbor, and that's because there's an edge from G to N. So it's sometimes backwards from how people might think about it, but that's the definition of adjacent or neighbor for a directed graph. So in this example, G is not adjacent to N. So G is not N's neighbor. Okay, but N is adjacent to G. N is G's neighbor. Okay, so there's an edge from G to N. That means N is G's neighbor. Okay. H is adjacent to J. H is J's neighbor because there's an edge from J to H. J is not adjacent to H. Okay, so the neighbor or the adjacency relationship goes in that direction. So again, the rule is vertex I is adjacent to vertex J, or I is J's neighbor, if there's an edge from J to I. Now back in this example again, N is adjacent to M, so N is M's neighbor, and M is adjacent to N. M is N's neighbor. That's because this particular edge goes in both directions. Okay, so you can have that happen where two vertices are neighbors of each other, but in a directed graph, a lot of times that won't happen. So again, here you could say that K is N's neighbor, but not the reverse of that. For the paths and cycles in a digraph, we do have to follow the direction of the edges. So this is an example of a simple path in a digraph. So this would be a path from J to M. So our path would go from J to H, from H to N, and from N to M, and that is following the directionality of the edges. So there's an edge that goes in the direction of J to H, and H to N, and N to M. Now, there are, of course, edges that connect J to K, but there is no edge that connects K to N. Even though it's an edge, it's in the opposite direction. So a valid path from J to M would not be J to K and K to N and N to M. That would not be correct because that does not follow the direction of the edges. So for your paths in a digraph, you always have to be taking that directionality into account and making sure you're following those directions. Now, this graph that we are looking at here is cyclic because it contains at least one cycle. An example of a cycle for this particular graph is the bidirectional edges. So we have an edge from H to N and an edge from N to H. So this edge goes in both directions, so that counts as a cycle. If we were to draw it a different way, instead of just using a single arrow, it might be easier to see that it was a cycle, right? If we use two arrows like this, then it would be easier to visually see that that's a cycle. So anytime you have a single edge going in both directions, that does count as a cycle. And if your graph has at least one cycle, then it's a cyclic graph. It only needs to have one to be considered cyclic. This has more than one. It has the cycle H to N and N to H, and it also has a cycle here. And I believe those are the only two cycles that are in this digraph. Here is an example of a digraph that is acyclic. So this is a directed graph that doesn't have any cycles. So if you kind of trace through all the various paths, you can get from M to H, but then can't go any further, from M to S, can't go any further, S to V, can't go any further, V to H, but you can't ever get back to M. So this graph does not have any cycles. Again, we have to take the directionality of the edges into account. So taking that directionality into account, this graph doesn't have any cycles, so this graph would be called acyclic. So if your graph does not have any cycles at all, it's considered acyclic. If it has at least one cycle, it's considered cyclic. And remember that for a digraph, you have to take that directionality into account both when looking at paths between nodes to see if there's a path that exists between two vertices rather, and also to see whether there's any cycles. Here's another example of a digraph. So it's a directed graph. The edges have a direction. This graph is also weighted. So in addition to edges having a direction, you'll notice that those edges have a weight. Now, each edge has a weight. And even though in our picture, let's say, for example, the edge from W to T and the edge from T to W is drawn as a single line with two arrows, it's actually two edges. It's an edge from T to W going this way, and it's an edge from W to T going this way. So in a picture, in a visual picture, this edge would have two weights. It has a weight going from T to W, that edge, and it has a weight for the edge going from W to T. In my picture, I just put the weight next to the arrow if it's associated with kind of the edge going that direction. So the T to W edge would have a weight of 2, the W to T edge would have a weight of 6. Sometimes you will see graphs still represented, weighted directed graphs represented with actually two arrows. So an arrow this way and an arrow that way, which can be actually a little less confusing. And if we were to do something more in depth with a directed weighted graph, I might represent it that way as well. But you might see it this way too. Okay, so you just got to be careful that even though here's another example. This looks like just a single line. It does have two arrows, so there's actually two edges there, and so there would be two weights. This particular graph that we're looking at is cyclic. It has at least one cycle, and again, those cycles have to follow the directionality of the edges. So this example that we looked at before, if we were ignoring the direction of the edges, then sure, we'd have a cycle. We could go N to H, and H to J, and J to K, and K back to N. There you go. That's a cycle. But that's not a real cycle because this edge we tried to go in the wrong direction. So this graph is acyclic. It doesn't have any cycles. This graph here is cyclic because there's a cycle that we can follow. We can start at T and go to S. That follows the direction. S leads to R. That follows the direction. R leads to W. That follows the direction. And W goes back to T. So this graph does have a cycle that follows the directionality. So this would be a cyclical digraph. Two other really important terms related to graphs are connected and complete. So connected, a connected graph means that there is a path to and from every vertex. Essentially, there is a way to get from any one vertex in the graph to any other vertex in the graph. A complete graph has an edge between every pair of vertices. So not just a path, but a direct edge, a direct link between every two vertices. For a directed graph, that means there would be V times V minus 1 edges if V is your number of vertices. For an undirected graph, there would be V times V minus 1 divided by 2. So that's essentially our undirected graphs are just an edge going in both directions. So thinking back about the examples we've seen so far, here's that undirected graph that we started with, undirected and unweighted. This graph is connected, but it's not complete. It's connected. You can pause the video if you want and take any two vertices, and there is a path to get you from one vertex to another. But it's not complete. Lots of examples why it's not complete. For one example, there's no direct edge from A to E. There's also no direct edge from A to F or from B to C. So it's not complete. But it is connected because even though there isn't an edge from A to E, there is a path because I can go A to D to E or A to C to F to E. So there is a path between every pair of vertices. This is the undirected weighted graph we saw earlier. This is also connected but not complete. It's connected because from any one vertex I can get to another vertex. So to go from G to M, I can go this way, I can go this way. to get from J to N, I can go this way, or this way, or this way. So lots of times there'll be choices. Sometimes there'll only be one way you can go. So back in this the example on the left, for example, to get from B to C, well, actually, there's two ways to do that too. I could go there or there. But sometimes there will be only one way to do it. You can take a look and try to find an example of that for yourself. But anyhow, both of these are connected but not complete. This is what a complete kind of version of this one on the left would look like. So this is the same one we just saw on the previous slide that's connected but not complete. If these same vertices, if we wanted to have a complete graph, this is what it would look like. So there is a direct edge from every vertex to every other vertex in the graph. Okay, so this has 1, 2, 3, 4, 5, 6 vertices. It's an undirected graph, so it has 6 times 5 divided by 2, so it has 15 edges, and that makes it complete. If it's complete, it's also by definition connected. But of course, we can have a graph that's connected but not complete. Here is an example of a non-connected or unconnected graph. So this is a graph that has 1, 2, 3, 4, 5, 7 vertices. So all of these vertices are part of the graph. It's just that some of them are not connected some vertices are not connected to other vertices. There is no path between them. So it's an unconnected graph. And of course, if it's not connected, it's definitely not complete. So this sort of subgraph is connected, but the whole graph is not. So there is no way to get from G to E. There's no way to get from F to G. Okay, so this graph is not connected. These are, again, all these vertices are in the same graph. It's one graph, but it's just that some of the vertices are unconnected or not connected. There's no path between some pair of vertices. And it might only be one. So pretend this graph didn't have these two vertices. Pretend this graph just had 5 vertices. This would still be an unconnected graph because there is at least one pair of vertices where there's no path between them. Okay? This is common in graphs. If you think about a really large data set, there are definitely going to be unconnected vertices. Okay, so it might seem strange because a lot of the kind of simple examples you'll see as you're learning graphs that are, visual pictures and textbooks and things like that will often be connected. But in a real situation in the real world of using data, it's very common to have your graph be disconnected or unconnected, not connected. Any way you like to say it. Now, what about a digraph? Again, a directed graph. So these are examples of undirected graphs and connectedness and completeness. But what does that mean for a digraph? Well, for a digraph, again, a graph with directed edges, for a graph to be connected, again, in general, it has to have a path to and from every vertex. But for digraphs, our edges have direction. So there's actually kind of 2 flavors of connectedness. You can say that a digraph is weakly connected or strongly connected. A digraph would be weakly connected if there is a path to and from every vertex, but only if you ignore the directionality. So you essentially treat it as if it's an undirected graph. A graph is strongly connected if there again is that path, but it follows the directionality. So it says you can only go across an edge if you're going in the direction of that edge. Now, most often when people are talking about connectedness with digraphs, they are talking about strongly connected. So if someone just says connected, it's a good bet to assume they mean strongly connected, but it never hurts to make sure and to make sure that everyone's using the same terminology. But most of the time, if someone's talking about a digraph and they say it's connected, they most likely mean strongly connected. It's rare that you would be talking about weakly connected because usually those directions matter. That's why you're using a digraph. So here's an example of a directed graph, a digraph, and this is weakly connected. Lots of reasons why it's weakly connected. One example, there's no path from G to J. So you can get from G to H, H to N, N to K, but there's no way to get from G to J. You could go G to N, N to K again, but there's no path that takes you from G to J. So that's why it's not strongly connected. Now, if we were to ignore all this directionality, pretend there were no arrows, then sure, it would be connected, right? So that means it's weakly connected. And again, this is usually not what we're talking about. Usually people are talking about strongly connected. So here's an example of a strongly connected digraph. So if you pick any two vertices, there is a path to get from one to the other. So if you want to get from S to V, you can just go S to R, R to W, and W to V. If you want to get from W to T, you can go W to V, V to T. So this is strongly connected. It is not complete because there is, for example, no direct edge from S to W. Lots of other edges missing too, but it's not complete. What about this one? So these are all edges that go in both directions. It is a directed graph because we were using those arrows, but all of our edges just happen to represent kind of two edges in both directions. So is this connected and is it complete? So yes, this is connected and it's strongly connected, but it is still not complete. So again, it's strongly connected because there is a path from between any two pair of vertices, and that path is following the directionality of the edges, so it's strongly connected, but it's not complete because again, there is no direct edge from S to W, S to V, R to T, lots of edges missing. In fact, this is what it would look like in order to be complete. And of course, if it's complete, by definition, it's also strongly connected. So there is a lot of terminology. That's a lot of words to throw at you all at once. But when you're learning about graphs, there is kind of this whole new world of terminology you're entering. So it's important to know the words, to know what we're talking about, and we can use those words to now create graphs and talk about them and describe them and look at their characteristics.